All right, so we're talking about the orbitals and the bonding in compounds, but whether you notice or not, we've also been talking about the shapes of the compounds. So think back to Gen Chem. The shapes of compounds is predicted by Vsepr, right? Vsepr stands for valence, shell, electron, pair, repulsion, right? So that's the way it's spelled. It's a funny spelling, but I think it's an acronym. Is that an acronym? I think that's an acronym. Vsepr, right? And basically the idea of Vsepr is pretty simple. It's that electrons want to get as far as possible from each other. So for example, if you have carbon dioxide, and if you're to draw it like this, right, all these bonds are made out of electrons, so they're the same charge, and so there's a repulsion here. And so they repel one another to get as far away as possible while still being bound to the carbon, and so what you end up here with is a linear shape. And so although we're talking about shape second, it's really the other way around. It's the shape that determines the hybridization, not the other way around. But they're very linked ideas, right? sp3 hybridized things will be tetrahedral, sp2 trigonal planar, sp linear, right? And so similar to hybridization, the shape is based on the number of things attached. But here it does matter what they are. So as you'll see, we'll treat a lone pair slightly different than an atom. And so for our purpose of our class, we're going to focus on the molecular shape. In general chemistry, you learned the molecular and the electron shape. We're mostly going to focus on the molecular shape. When we're talking about the shape of water, for example, we're going to say that it's bent, not that it's tetrahedral, because we're talking about the molecular shape. So let's see the most common shapes we'll encounter, and that'll be 4 atoms attached. An example of this is your good old carbon with 4 hydrogens, your tetrahedral carbon, right? So it looks something like that. Hydrogen above, hydrogen kind of bottom left, one coming out of the board, one going into the board, and this shape is tetrahedral. And this bond angle here is approximately 109.5 degrees. And so then we can talk about another thing that has 4 things attached, but in this case we have 3 atoms and then 1 lone pair. And so then an example of that is NH3. So we'll have this nitrogen with this lone pair and then 3 hydrogens attached in a tetrahedral fashion. But now since we're talking about the molecule geometry, we're not a tetrahedral anymore. Now we are trigonal pyramidal. And remember that the lone pairs repel more than a bond. And so this bond angle here is actually less than 109.5 degrees. And then finally, we have a situation in which we have 2 atoms and 2 lone pairs. Example of this is water. With the oxygen being connected to 2 hydrogens and then 2 lone pairs. So we have this oxygen here, hydrogen, hydrogen, and then we've got 2 lone pairs where one of the lone pairs is kind of going out of the board and then the other lone pair is going back into the board. And so we say this shape is called bent, where this bond angle here is less than 109.5 degrees. And so you can see that all of these things have 4 things attached. So all of these central atoms are sp3 hybridized. When you're sp3 hybridized, you'll have that electron geometry of tetrahedral, but your molecular geometry might be tetrahedral, it might be trigonal planar, or it might be bent. Next up, we have this kind of 3 atoms approach, something like BH3, right? We have this boron, H, 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 and then this shape right here is trigonal planar, where each one of these bond angles is 120 degrees. Another example would be this carbon, right? It's actually both the carbon and the oxygen are both trigonal planar, are both sp2 hybridized. They both have 3 things attached. And so this central carbon, this central carbon is trigonal planar. But all of these atoms are actually sp2 hybridized. This boron, this carbon, and this oxygen are all sp2 hybridized. And then finally, we have a situation in which we have 2 atoms, something like BeH2 or acetylene. Right. Both of these shapes are linear, and thus these bond angles are 180 degrees. And all of these central atoms, this beryllium and these 2 carbons, are all sp hybridized. So you can see that hybridization, shape, and bond angles are all interwoven and essentially talking about the same thing. The only thing that differs is the shape and the hybridization when you're talking about, okay, what are those things? Are those 4 atoms or 3 atoms and a lone pair or 2 atoms and a lone pair? That kind of thing. But overall, it's essentially the same concept.